Hi everybody, welcome to my demo. My name is Jonathan Malavi and this is my project. This is a piezoelectric contact microphone, and basically what it does is it senses physical vibrations from within a solid object and converts it into an audio signal, which is then amplified and made suitable for any regular everyday audio interface. As you can see, it just terminates in a regular old headphone jack. Now, it's probably worth mentioning that this is not a typical air microphone that we're used to. This is a contact microphone in that it transduces vibrations from solid objects, not air vibrations. Now, the way it's able to do this is through this piezo disc. Actually, that's separate from the circuit. Here we go. And really all this is a metal disc with a thin film of piezoelectric ceramic material on top and just two contacts soldered onto it. What I mean by piezoelectric material is that this ceramic material creates a voltage in response to physical stress. And this voltage, if you were to say fix it to a surface, it would essentially create an audio signal. And if this were an ideal world, I'd simply be able to plug this into the speaker and crank up the volume, and that would be that. But unfortunately, it isn't that simple. The piezo disc has a very high output impedance and generates almost no current because of that, even though it's creating a voltage. So the solution to that, or I guess a solution to that, is just a simple preamplifier circuit using a JFET in this case. The reason I used a JFET is just simply because I had some lying around, and they have high input impedances, so it's pretty much perfect for what we have. And yeah, here's the schematic for it.
Okay, so without going into too much detail here, the amplification of the circuit occurs in this MPF102 transistor right here, and it's in a common source arrangement. The input voltage arrives at the gate and the output voltage leaves at the drain, and it acts as a voltage controlled current source. And basically, to explain the way the current behaves in this circuit, when there is no voltage to the gate, here's what's called a zero gate voltage drain current, abbreviated as IDSS. And I designed this circuit to have an IDSS of about 5 milliamps. And when you start applying a voltage to the gate, that's when things start changing. A forward bias to the gate cause an increase in current, and a reverse bias will cause a decrease in current. Pretty simple, but we don't really care about the current. We care about the drain voltage because that's our output. And if you're to consider Ohm's law, an increase in current essentially corresponds to a decrease in resistance, and consequently a decrease in the drain voltage. So a forward bias on the gate will result in a decrease in drain voltage. So in essence, this is an inverting amplifier.
Alright, so without further ado, I will now demonstrate the circuit in action. As I previously mentioned, the circuit uses 15 volts DC as power. I designed this using an adjustable power supply in the lab. I don't have this luxury at home, but what I do have is this random 15 volt wall wart, which is probably older than I am, but hey. Plug that in. And plug in the speaker and we'll be good to go. And just in case there's any doubt that this is actually me, alright, so nothing left now but to just test some objects. Here's a few that deserve to be pretty good. And just so we're clear that this is an actual amplified noise, yeah. Comb. And last but not least, how about that ugly mug?